Hi, Conrad. Welcome to this episode of Edu Trends Podcast and Webcast, produced by the Institute for the Future of Education of Tecnológico de Monterrey. We are very happy to have you here and to talk matters regarding math, technology, and data in education. So to start the conversation, Conrad, I would like to ask you, why do we keep failing to change the way we teach math?
It's a great question. Well, firstly, thanks for having me here today. It's very nice to be able to do this and sort of transnationally as we can today. A great success of modern computational technology. I think that education is very much in a sort of stuck ecosystem in terms of change that we need rapidly and change that the outside world should be forcing on us. And we can go into why this might be. So I think maths is at the epicenter of that because it's the most, apparently quantitative and tested and important in many ways for many people's view. And therefore, it's very, very hard to make changes because any change you think you might want to make, there are many, many people who think, oh my goodness, no, we can't make a change. I think the other thing I would say at the outset is there are two very different aspects of change that we need to separate in our thinking. One is what I think most people talk about most of the time when they think about AI and data science with respect to education, which is how we change the process by which you learn, the pedagogical process of learning any subject, maths or any other subject. The change that I've been most interested in is how the subject itself needs to metamorphosize because of the changes to that subject in the outside world. Not how we teach it so much as what the subject is, what the modern subject is. And that's because in the outside world, the modern subject of mathematics is very, very different to what it was 20, 30, 40, 50 years ago. And it's also perhaps much more important to everyday life. So I would separate those two, and I think one needs to think of, they're intertwined, but we need to think of those quite differently if we're to really address some of the problems that we have at the moment.
Thank you. So you said that a very interesting statement that math is at the epicenter of everything. I think some people may disagree with that, and I would like you to elaborate around that.
Sure. So let me clarify a little bit. I don't mean that necessarily it ought to be. I don't suggest maths is more important than many other subjects, which I think are very important. What I do suggest is that when you think about admission to university, if you're at school, or how people think, many parents and things think is important when they look at exam results and things that measure performance in education, mathematics comes very, very high in the list, and that's for several reasons. Firstly, it's a compulsory subject up to, school level in most countries. Secondly, it appears to be very measurable, very objective, rather than subjective. I'm going to come back to that. I don't actually think that's true in how we measure it, but that's a different question. But it appears that way. And so the pressure to succeed at mathematics in many countries is very, very high. And that causes all sorts of trouble. I mean, so for example, I don't know if it's true the same way in Mexico as it is, for example, in the UK, but there are all sorts of courses that you might want to take at university that require mathematics to a reasonably high level at school. And you ask, why is this the case? And often it's not very obvious. It's like, well, in order to study biology, for example, do we really need traditional mathematics education the way it is at school? Does it really tell you much about how good a biologist the person's going to be? Traditional mathematics education at school doesn't really cover data science in a modern way. It's got very little to do with modern data science. So therefore, it's not really telling us whether they'll be good as computational biologists. So we've got all these intertwinements of maths. So that's why I say maths at the epicenter, because for many people, it's actually causing them not to be able to succeed at what they're interested in because they're not allowed to even go there because their qualification in mathematics is not sufficient to allow them to that step. And so reforming mathematics actually unlocks for many people a reform of what they can do, how we think about education, what we think is sort of intellectually important. And I'll give one quick example. I mean, and again, I don't know the situation in Mexico as well, but in Europe and certainly the UK, in the 50s and 60s, 1950s and 60s, you had to have a Latin A-level, the qualification you take before you leave school, in order to be allowed to study at a top university. Pretty much universally, depending, independent of the subject you were studying. Now that seems crazy. Why would you need to learn Latin to be able to study physics? And it was just like a measure of intellectual ability somehow. Kind of got ingrained that somehow Latin was the measure. And if you weren't good at Latin, you were not intellectual. And I think we've got the same problem with mathematics in the current way in which it's thought about in much of education. And so that's why I say it's so much at the epicenter at the moment. Now, as I'll say, I do think there is a very important subject a bit like that actually should be more at the epicenter, but the current subject seems to me misplaced for that.
Thank you. You also said that what we teach in schools as a subject, as a discipline on math, what we teach in universities, it's like it doesn't reflect the maths that we did in today's world. Can you elaborate around that? What do we need to teach?
So we've confused the art of calculating by hand with the bigger subject of what I'm going to call computational thinking. Call it mathematics, you can give it various names. But in the end, there is this incredibly empowering, more or less 4-step process that has been developed over hundreds of years to allow us to work out answers very precisely to questions we have. And the big fundamental change in the last few decades is we have machines that now do the calculating step of that, which I'm step 3, I'll come back to that in a moment, and do that far better than any humans could ever have imagined being able to do that. I mean, the machinery is just the most extraordinary machinery mankind has ever invented. It's surpassed anything that anybody might have predicted. So that's what's happened in the real world. That machinery has meant that we can now apply computational thinking or mathematics in the real world to a huge variety of areas. And we see this every day. We see it to pandemic modeling. We could never have had that as a general purpose thing in the way that we do now. Too complicated, needs too much calculation. We see it in every area of life, that we have a computational way of thinking about that in a way that we didn't 50, 60, 70 years ago. So the big change, the big difference, the big issue is in certainly school education around the world, we spend 10 plus years educating our students how to calculate by hand. And in real life mathematics or computational thinking, what we actually do is we have a computer to do the calculating by hand, and we need humans still to set up the problems, to translate them from English or Spanish or whatever into the algorithmic approach that allows us to then compute precise answers. Then we need to interpret the results, make sure they're accurate, they fit the problem, we don't get misled, all of those steps. So really this 4-step process is, define the problem, change it to, in a sense, maths, which, by the way, today isn't usually program, it's usually code for a computer. That's how we're abstracting the problem out. That's part of this amazing process to be able to abstract it. Then we're doing step 3, which is take the question in abstract form and turn it into the answer in an abstract form. That's the step that computers can really, really help us with. And then step 4 is, we say, well, okay, x equals 3 or whatever. What did that mean? That meant it answers this question that we asked to start with in a particular way. And does that make sense? Does it not make sense? Do we have to run this process again in some way to see if we get the answer? That's the process. We're concentrated on completely wrong part. It's almost like an 80-20 split. We spend 80% of our time hand calculating at school. And yet in the outside world, virtually nobody does hand calculating for anything. But they do set up much, much harder problems at a much higher level on much fuzzier issues. And that's what we don't have any of basically at school. And so people are very ill prepared for that real world utility.
Yes, I agree with you that steps 1 or 2 maybe are the most important right now because they are not addressed correctly in education. In particular, the first one is very interesting because of the difficulty sometimes to identify the problem and define the problem, and maybe have even an agreement that that is the problem because some situations are so complex, no? And is one of the reasons why students cannot translate what they have learned in school to complex real-world situations.
Yeah, I mean, no experience is the reason. I mean, so I suppose my view of education in general is, I mean, you can argue what the point of education is, and thousands of years of argument over this, and many different philosophers and so forth. I mean, I suppose my outer statement on this is to say education is to enrich life. I mean, to enrich it, not just in Richie's, not in just making money, but in your meaning of life that you see, and also societally in the meaning of life for that society, to make it, more purposeful in a sense. And I think that one great way of the process by which education sort of works in a way is to give people accelerated experience of the sorts of issues they may face in life. I mean, not necessarily purely mathematical or anything. I mean, it could be, ways to handle stress, or it could be how you think about different problems. But I think computational thinking is a very important strand of that experience that you need. How do you address problems in a computational way? And we see this very much. I mean, everybody's fed up with the pandemic, but you see this in, should I get vaccinated? What should I do? Do I trust the government data? Do I understand the government data? Does it make sense? Are we talking about infections, or are we talking about serious infections? These are different definitional ways we might think about it. They're very critically different, et cetera, et cetera. So there are very big issues that nowadays are discussed in a computational way, and were not a number of years ago. And the real thing I'm concerned about across society is, if we don't have majority of society ability to be computationally literate, at least, it means that a lot of society can't partake in most of the decisions that are being taken, which have a computational basis. And it's a bit like, I've been comparing this to, in the past, before mass literacy. I mean, if you look back to, the early 19th century, there was a big argument about whether it really made sense to have most people be able to read and write. There were a lot of people who said, most people are too stupid. There's no point. It's, you just need a small elite at the top who can do this stuff, and everybody else can follow. And that's, I think, one of the biggest successes of mass education has been literacy and the ability for most of the population to partake in reading and writing, and therefore to be able to form their own views, to be able to look at stuff themselves. Now, I think we're in a new era where what we critically need is, so to speak, computational literacy, and the ability for most people to be able to partake in these computational discussions and understand enough and be able to reason enough in that way that they can benefit their life greatly. And I think we don't do that, we will see more and more bifurcation in society, because people will not be able to be part of that. They'll just be a top echelon, and then there'll be everybody else.
Yes, so that's once again an argument for the importance of math or computational thinking. It seems that you use them as synonyms when you talk about math and computational thinking. Am I right?
Not quite, but here's the difficulty I have, and I've wrestled with this for a decade. So what I think of as mathematics, I've renamed as computer-based maths as being the modern version of this subject. And I would be quite happy to call it. After all, our main software that our company makes is called Mathematica. And in fact, Steve Jobs of Apple came up with the name originally. So we are very associated with that word mathematics. Unfortunately, many people really, really dislike the word. And they have all sorts of very negative connections with that. And actually, if you look in the outside world now, subjects that really are mathematical, as I would think of them, don't have that word attached. Like there used to be mathematical physics, but now it's computational biology and computational this and many other ways. People have avoided the math word. The math as a term has become rather specialist into people who literally invent new bits of mathematics. So I've had some difficulty when we talk particularly about school reform, because there's a lot of money and effort and time spent in mathematics. So in a way, you'd like to move that to a new way. But the alternative is to kind of introduce something new called computational thinking or something like that, which has the advantage of being new, so you're not battling a tradition that may be stuck. So I don't entirely use them interchangeably, but I've got to using them more and more that way. And I'm afraid that what worries me is I don't want, so to speak, the brand of maths to pollute the change that's required. just to stick with that name, though I do quite like the word, but that's, I prefer to sacrifice the word than the subject in a sense.
Yeah, to avoid sometimes like a instant reaction of fear or stress around math, no?
Yes, that's right.
So talking about technology in education, in particular in math and science, there's a lot of hype of artificial intelligence right now. I myself did some studies in artificial intelligence back when I was in school, and we have always talked about the promise of artificial intelligence, and then it doesn't always deliver. Do you think that this is the time for artificial intelligence to deliver in education, and why?
It's a very complicated picture because it depends what you're trying to deliver with it. So is it true, for example, that many more students could take a much wider range of subjects and fields by having it available with a computer, including having intelligent adaptive learning that helps them? Yes, I think it is. I mean, instead of having to be at a very special school to be able to study ancient Greek, if you happen to be interested in ancient Greek, it would be nice if you'd be able to have a tutor that's online, maybe mixed human and artificial intelligence, which will move you to a next step without the human having to be there all the time. So there is clearly possible promise in that. The difficulty is what keeps happening is when it's particularly confused with how we assess people. So I think we are, in many parts of the world, obsessed with assessment and with trying to measure people all the time. And one thing that goes very badly wrong there is people want ever more quantitative measurements. Did you get an A or this percentage in your mathematics exam? And the problem with that is you then end up with questions that are easy to mark. And artificial intelligence tend to push us to make questions that the computer can easily mark. So you say, well, it's great. I can set people lots of tests. They're very easy. We don't need too many humans. They can go on getting marked. But then you end up making tests which are very, yes or no, a particular number is the answer. And we tend to be driven in this way. Now, what we really need to be testing in people is their ability at open-ended problem solving, which is what they actually face in real life. And their ability to be able to reason through that, write down some reasoning, communicate it well, including to other humans, including to computers. And the trouble with I think some of our technology at Wolfram Alpha does help with this, but it's a long way off what a human can do in analyzing that. So I think when we say we want artificial intelligence to help, that there are many, many ways we can move forward on this. But I don't think it's a blanket positive. And I think we shouldn't think somehow it can replace human teachers, because I think that simply won't work. I think what we need to do is shift what human teachers are focused on. They need to be focused on sort of being the CEOs of the classroom, in a sense, rather than the fountains of knowledge. We have the knowledge from the web and in computers. We can help with that. The teacher needs to be very much more guiding and qualitative in how they're working with the student as much as possible. So it's a qualified, I think we'll see improvements and we'll see ways we can move forward, but I don't believe that it's sort of some kind of replacement that really somehow gets humans out of business on this one.
Yes, I also agree that the human touch and the qualitative assessment that a teacher can do will never be substituted by technology or artificial intelligence. And I understand that what you are saying is that in general, we are the model that is inside these artificial intelligence engines, like an adaptive learning program for math teaching. It's based more on the objective part of math that doesn't cover the first 2 points of your 4 steps, no? So
or the fourth, yeah.
Sorry?
Or the fourth part, or the verification and understanding, or it covers, you're right, it covers basically the calculating step 3 and pushes people to ever more do calculating problems.
So that means that it's impossible to develop a system that helps in other parts, and that also means that teachers can benefit of these adaptive learning tools as an addition to enhance math learning, or you don't think they are necessary?
No, I think there are very different ways to. So I wouldn't say never, right? I mean, I think these things move forward, and 100 years ago, people would say you'd never have a calculating machine that outdoes a human, and yet we can do that many times over now. So I would never say never, but I don't think that's the immediate. I think it'll be a long time, longer than you think. It's like getting a self-driving car to drive around London, or Mexico City, right? It's a tough job to get a self-driving. It's easy enough on a Californian freeway, perhaps, but on in Mexico City, I'm sure in London, it's not so easy with other humans around, right? So it's a bit the same as that. I don't think never, but I think it's slightly further off than people might imagine. But I think that, for example, we have built in computer-based maths, we've been trying to work out how do we manifest this curriculum that we've been building. I mean, what do we do? What do we deliver to teachers and students to actually help them? Because we've been trying to work out from the scratch, assume computers exist. What would the mathematics or the computational thinking curriculum look like? What do you teach them? What subject matter do you actually have? And so what we concluded is we want to start from complex problems, which we think might be interesting to the student. I mean, our first problem set was called, Am I Normal? Can mathematics help me figure out if I'm normal for my age group? Do I have normal height and foot size, or, am I not? And what does that mean? Does normal, how you define normal? Is it one variable that's different, or two that are less different, or what does it mean? And other things, is it, can I spot a cheat if I look at some of the data they're producing? These kinds of questions are messy questions, but kind of interesting, we hope. And then what we want is we want the computer to be there ready, but you can't just give people a blank screen and tell them to work with it. They've got to learn a bunch of stuff. So we have a very guided set of problems that they can work through. Now, you need a computer with interactivity, with modern graphics, with ways to show them to help guide through this. You want a high-level language. So I don't know whether you call that artificial intelligence exactly. Some of it is, some of it isn't. But those things absolutely are essential because we have those in the modern world. And we need to replicate the best tools initially for a student when they're learning. I mean, this is another weird fallacy I was thinking in education. To me, if you're learning something brand new, that is the most critical time to have the very best tools for the job. When you know the subject really well, you can get away with worse tools because you're already able to handle the subject in such a way that not so good tools are still usable by you. But that's the wrong, don't mess up the students' initial learning by giving them very hard to use tools. So I think we need the most powerful computers and tool sets so that they can work at the highest level and try and interact with difficult problems. So I think it's very much combined in that. You need the modern tool sets. We have the modern artificial intelligence and data science. We need to use those in education as part of the subject matter where we're trying to educate the students in.
Thanks. So in order to teach the new kind of math that we need for the modern world, it is necessary for teachers, for instance, in higher ed, to use a set of data in class, or how do you bring that new kind of subject of math to the classroom so that the students can develop those skills?
Yeah, I mean, if you talk about higher ed, I think there's some interesting questions about how you organize the subjects. Because I think my view of this is almost every subject, there's a computational version of that subject that you can now teach or should be teaching in parallel. I mean, it depends. We talked about biology earlier. There's obviously computational biology is a relatively modern area of science, but it's extremely important and prevalent. Obviously, computational mathematical physics has been around for many, many years. But then there's also computational law, for example. There's computational history, where you analyze history. It's not that you don't analyze history in the way you've done it before. This is additional. You think about history from can I analyze history in a sort of computational way of looking at the past? And one very simple example we had is, you could, for example, try to analyze what US presidents said in their inaugural speeches and try and work out what they actually did in the 4 years afterwards to see whether it matched the words that they were used and what the correlation is between those. I mean, there's all sorts of interesting things you can do, which you wouldn't do traditionally in history, let's say. So I think in universities, it's very important for there to be the ability to do modern computational pieces or options for all of those courses that were traditionally not computational. Then there are, of course, subjects that are purely computational, are born out of computation, like computer science is obviously a subject that's been born of the computational era. And then there are subjects where it's evolved. Physics. I mean, physics we should be doing stuff with millions of data points, not with traditional, ways that we did bits of physics. I mean, there are traditional bits of physics, they're very important. There are modern bits of physics with mass data and different ways we approach things. My brother works in complex systems research, which is born out of the computational era, for example, in physics. So we need to imbue those. Now, then there's a separate subject. What is the core subject that can help with all of these? Because just telling a student, who doesn't really know how to do computational thinking, go use computation for history is unlikely to work straight out of the box. Traditionally, we've had maths as a supporting subject run by the maths faculty. That's one model, but it really needs to shift a lot into a very different subject with huge amounts of data, complex models, very different sets of things that you end up doing to start students and to move them on. So it's a very radically different sort of course. And we've been working with universities and countries and things to try and exactly map out what that should be. But so I think there are two shifts. There's this sort of core subject shift, and then there's the shift of adding computation to these other subjects. And I think universities in particular higher education needs to think very, very hard about how to do this, because I think this is a major shift happening now. And organizations like us who hire people absolutely want to see that. And we're not seeing some of the thinking coming out of the students that we really need to be able to solve the kinds of problems and make the decisions we make today using computation.
Yes, I can see what you said. For instance, in our School of Government in Tecnológico de Monterrey, data science is becoming increasingly important. And maybe even 10 years ago, you wouldn't think of using data science for, I would say, public policies, for instance, no?
Yeah, indeed.
So it's
yeah, that's a very good example. And I also think, it's funny because there are actually straight computational things like using data. And then there are issues like cause and correlation. What's caused what? Can I push through those sorts of arguments in a sensible way? And most people in the population have rather poor skills in those areas because they haven't been taught them in any real way. So I think it's really important to have this very broad view, and also where different things work. We hear about machine learning all the time. Where is machine learning useful? Where does it fail? It's a technique like many other techniques. There are, all sorts. It's a very powerful new technique born out of the computation, about modern computer age where we have lots of computational power. But it's not the only game in town, and it has huge errors that can set in certain cases. That's the sort of knowledge we need folks to have, even if they're not this specialist data scientists. Otherwise, they'll get misled. If they're running government policy, for example, you can imagine how difficult it is now to understand the different proposals and ideas and suggestions for policy that come out if you have no grounding in how you may be able to cross-examine the advisors and other people who are giving you this policy. So that is a very critical part of our decision-making process today.
Exactly. Now, for instance, it reminds me of the importance of understanding that if the data set that you use for machine learning is bias, you will get bias result on machine learning. Remember this program that was used to decide if someone can have the legal process in jail or on the street was biased because they were using data that was ethnically biased, no, by the person
I see. Yep.
that did the decisions, no. So you are automatizing that bias into the machine. So you have to understand those kind of things also.
Yeah, and you see, I think it's a really good example. And the only way you can build experience of that in the population and decision makers and managers and everybody else who has to affect what happens to everyone is really by them just gaining it over a period of time, by running actually complicated problems. If you give them 5 data points to plot on a graph by hand and draw a curve through it, they're not going to get that kind of experience because it doesn't come up. It comes up when you've got millions of data points in a real messy problem. As you say, in that case where you've probably used machine learning in a case where maybe you shouldn't have done, maybe you should have used an algorithmic approach, or not, it depends on the situation. But you need to build experience of all of that kind of thing in order that we don't easily get misled. And it's pretty hard won. I mean, this experience is tough to get in. I mean, it's I think intellectually extremely challenging. And one of the things that frustrates me is when we have politicians in particular who say, oh, somehow it's all going to be easier if we just let them use a computer. They won't use their brains. I say exactly the opposite. I think if we have messier, harder problems because we can use a computer, it's actually much more intellectual and much more of a conceptual brain training exercise than, in a sense, humans are stepping up to the next level rather than sitting on a more mechanical level that we now have machines to do.
Yes. Yeah, we can keep the part that is more messy, wicked for humans, no? So that's the way that things are changing. Well, we are arriving to the end of our Edu Trends interview. Thank you, Conrad, for your time and for sharing with our audience how we can start changing the way we see, learn, and use math, and I would say computational thinking and data, not only at school, but as you said, in our lives, to make them more rich, to enrich our lives. This talk has been really interesting and enjoyable. I will surely be of great value to our audience. We look forward to talking about data, STEM, and math with you again. Thank you, Conrad.
Thank you very much.